An introduction to logic gates. Prior to the invention of electronic gadgets, mathematicians and philosophers were unwittingly inventing the binary language and establishing the groundwork for contemporary computer technologies. These ideas were eventually applied to comparable communication methods such as Morse code and binary, which we are all acquainted with today. Mathematicians like as George Boole and Charles Babbage used these principles to automate mechanical equipment. Let's move on to the history of ancient logic and binary. During the 10th century, a scholar named Xiao Yong reorganized the hexagrams from the I Ching into a binary-like structure. Some academics believe that Gottfried Leibniz was inspired by the I Ching while developing binary coding. In ancient Greece, truth tables included yes and no buttons that functioned similarly to on and off switches in transistors. Leibniz was most likely inspired by Greek mathematicians since their writings were the most accessible to European scholars throughout the 17th and 18th centuries. From mechanical to digital logic. Although Gottfried Wilhelm Leibniz is credited with developing binary as we know it today, Charles Babbage was the first to develop logic-based machines. His original difference engine was a mechanical calculator that tabulated polynomial equations and printed the answers onto a roll of paper. He planned a second difference engine, sometimes known as the analytical engine, which were recognized in 1980s, and a fully working model was ultimately constructed to his specification. Electromagnetic relays, which were essentially on and off switches, were the first common logic gates. Joseph Henry created the electromechanical relay in 1835, which were utilized in a telegraph. Nikola Tesla submitted a patent in 1898 for an idea he named teleautomation, which he demonstrated using a radio-controlled small boat, the first remote control device ever constructed that included a mechanism for decoding Hertzian waves that acts as an AND gate. The logic circuitry of the earliest digital programmable computing systems was built in vacuum tubes. This includes well-known machines like as ENIAC or ENIAC, Colossus, and Alan Turing's Pilot Ace. During the 1960s, the introduction of resistor-transistor logic or RTL and transistor-to-transistor logic or TTL, which resulted in the much-needed reduction in size. RTLs were the first logic devices to be introduced onto integrated circuits and were later utilized in the Apollo guidance computer. Now, let's talk about the logic gates. Logic gates is said to be the heart of digital electronics that acts as the basic building block of digital circuits. A gate is an electronic device which is used to compute a function on a two-valued signal. According to IDRA.com, logic gates are small digital electronic devices that perform a Boolean function with two inputs and provide an output. The data are the binary ones. Logical 1 is true or high, and logical 0 false to false or low. Based on the logical gate, the logical operation differs and the output varies. Each logic gate follows a truth table that gives the possible combinations of input and respective obtained output. These are the types of logic gates. So how do they work? A logic gate's function is expressed using a truth table. It depicts every conceivable input-output combination, and a column next to each row gives the matching output value. With any number of inputs supplied, a single output with a time delay is produced. We have the first type of logic gates, the NOT gate or the inverter. The output of NAT gate is high if the input is low and vice versa. The next type is AND gate or multiplication. The output of AND gate is high if both the inputs are high and the output is low if both or either of the inputs is low. The third type is OR gate or addition. The output of OR gate is high if both the inputs are high or one of the inputs is high. The output is low if both the inputs are low. The next type is NAND gate. The output of NAND gate is high if both the inputs are low and if either of the input is low. The output is low if both the inputs are high. Next, we have NOR gate. The output of NOR gate is high if both the inputs are low. The output is low if both the inputs are high or either of the input is high. SOR gate or XOR gate. The output of SOR gate is high if either of the input is high. The output is low if both the inputs are high or if both the inputs are low. Lastly, we have XNOR gate. The output of XNOR gate is high if both the inputs are high or if both the inputs are low. The output is low if either of the input is low. So, do you think logic gates are that important in today's era? Well, the answer is a big yes. Centuries of research have resulted in tiny and powerful logic devices such as FPGAs, PLCs, and Pico gates, which enable tiny devices to have computational capacity and control capability that dwarfs the huge machines of before. There are small logic packages for almost any function imaginable these days, whether it comes in an array or a single package. And today, we are using the product of all of their curiosity, eagerness, and hard work, and that's what makes our technology today.